Here we're going to look at question 14 from section 2 of the ENGAA 2018 paper. In this question we're given three blocks, P, Q and R. We're told that Q and R are connected by an inextensible string which goes around this pulley which is connected to the mass P. Each of the blocks have masses shown on the diagram, and then we're told that block P is accelerated with an acceleration A, and due to this acceleration Q and R are going to be stationary relative to P. Then the question asks us to find the acceleration of our block P. If you would like to have a go at this question yourself, please pause the video now, otherwise let's have a go at it. So let's begin by just thinking about what's actually going on in this scenario. Now we're told that this big block P is accelerating at this rate A. Now this means, we're also told, though, that Q and R don't move relative to P whatsoever. So this means that R must also be accelerating in this direction at a rate A, and Q must also be accelerating in this direction at a rate A. But so how is that going to work in this scenario? Because if we just imagine the block stationary and not accelerating at all, then R would fall and A would move this way. So our block Q would be accelerating. You would think then perhaps that if P was to accelerate, then Q would just accelerate kind of independently of this of this block P, since there's no friction between these surfaces at all or anything. But what's actually happening here is that the acceleration of Q due to this block R is going to be exactly the same as A, exactly the same as the acceleration of this block P. So this block P is accelerating, and this block Q is accelerating at exactly the same rate. So they're going to move they're not going to move relative to one another at all. They're just going to stay in exactly the same positions. So this might seem a bit weird, but to Q, what's basically happening is that R is sort of falling forever. It's just going to consistently stay at the same height, but it's going to keep pulling down with the same force, which is going to keep trying to pull Q this way, but it's never going to actually move closer to the pulley because the pulley is moving away from it. Now, with that cleared up, perhaps we can go on and think about the forces on each of the blocks. So let's consider the mass R first of all. Now, what we should think about here are probably the forces which are going to be relevant to our other block Q. So we're going to have two forces on our mass in this direction along the spring. We're going to have this tension here in the string, and then in the opposite direction we're going to have this weight. Now we are also going to have a force pushing this way and a reaction force into P, or a reaction force due to P, which is going to accelerate our mass R in this direction. But there's no point really enabling this on, since it's not actually relevant to our mass Q whatsoever. So for now, let's just stick with these two forces. If we go ahead and do the same thing for Q, then we know that it's got tension along this string, but there's no frictional force whatsoever. So the only force we have is this tension. Then just a single force on a mass should probably make you think of acceleration, and as we said earlier, the acceleration of Q is just exactly the same as the acceleration of our big block P. So this tension is producing this acceleration. Now with this in mind, let's go ahead and write down some equations relating these forces together. So if we consider our block R first of all, then we know that this block isn't moving relative to P whatsoever. So these two forces are in equilibrium. Our tension is going to be equal to the weight of our block, our mass R, multiplied by the gravitational field strength G. We can then go ahead and do the same thing for our block Q. And then using Newton's second law, we know that the tension in the string is going to be equal to the mass of the block multiplied by its acceleration. So with these two expressions, we can go ahead and eliminate T from them by equating them to one another or dividing or any other means. And then if we divide through by mq, then we get the acceleration of our blocks of Q, of R and P. They're all going to accelerate with the same rate to the right. This acceleration is going to be equal to the mass of R divided by the mass of Q multiplied by G. So we can see that this answer corresponds to B given in the question.